Welcome to a lesson on compound inequalities. Let's begin by defining the intersection and union of two sets. The intersection of two sets A and B is the set of all elements that are contained in both set A and set B. As an example, if we let set A equal the counting numbers from 1 to 7 and set B equal the counting numbers from 5 to 10, we express the intersection of set A and B using this notation here, which is equal to the set containing 5, 6, and 7, because 5, 6, and 7 are the elements or numbers that are in both set A and set B. When two or more inequalities are joined by AND, it is called a conjunction. When solving compound inequalities for the word AND, we look for the intersection of the intervals. The union of two sets A and B is the set of all elements that are contained in either A or B. So if we define set A and B as we did before, then the union of set A and B, expressed using this notation here, would be all the counting numbers from 1 to 10, because the counting numbers from 1 to 10 are either in set A or set B. When two inequalities are joined by OR, it is called a disjunction. For compound inequalities, for the word OR, we look for the union of the intervals. To emphasize the difference between the word and or, let's look at one more example. If you are told you will be happy in life if you make a lot of money and have a rewarding personal life, because of the word and in this case, both conditions must be true to be happy. However, if we change the word and to or, and the statement reads, you'll be happy in life if you make a lot of money or have a rewarding personal life, because of the word or in this case, only one of the conditions must be true to be happy. Let's solve some compound inequalities. Notice for this first inequality, we have a variable in the middle and then an inequality to the left and the right. This compound inequality always represents two inequalities connected by the word and. Starting in the middle, we can read this from right to left as x is greater than -2, and starting in the middle, reading from left to right, we have x is less than or equal to 5. Now let's graph both inequalities on the same number line, and because we have the word and, the solution is the intersection of the two intervals. For x greater than -2, -2 is not in the interval, we make an open point on -2, arrow to the right. For the second inequality, we have x less than or equal to 5. 5 is in the interval. We have a closed point on 5, arrow to the left. This graph is not our solution. We need to interpret this. Because of the word and, we are looking for the intersection of these two intervals, which would be the numbers from -2 to +5, not including -2, but including +5. And therefore the solution would look like this. To express this using interval notation, the interval goes from -2 to +5. The interval does not include -2. We have a parenthesis to the left of -2. It does include 5, and therefore we have a square bracket to the right of 5. The next compound inequality is obviously an OR compound inequality. The first step is to graph the two inequalities. Let's graph one in red and one in blue. X is less than -2. -2 is not in the interval. Open point on -2, arrow to the left. X greater than or equal to 3. 3 is in the interval. Closed point on 3, arrow to the right. Now we're looking for the union of these two intervals, which means we combine these two intervals to determine the solution, which means this is the graph of the solution. But let's go ahead and graph it in black. The final graph has an open point on -2, arrow to the left, and a closed point on 3 with an arrow to the right. To express this using interval notation, we need to recognize to the right we approach positive infinity, to the left we approach negative infinity. For the interval to the left, we have the interval from -infinity, -2. Neither endpoint is included, and therefore we have parentheses around negative infinity and negative 2. And then we use a capital U for union. The interval to the right is from 3 to infinity. The interval includes 3, and therefore we have a square bracket to the left of 3. And for positive and negative infinity, we always use a parenthesis. Let's look at another example. Again, looking at the compound inequality, we have a variable expression in the middle, and then an inequality to the left and to the right, which means this represents two inequalities connected by and therefore we will look for the intersection of two intervals. Reading from right to left, we have x plus 2 is greater than negative 5, and starting in the middle, reading from left to right, we have x plus 2 is less than or equal to 4. And now for both inequalities, we need to solve for x by subtracting 2 on both sides. Subtracting 2 on both sides here and simplifying, 2 minus 2 is 0, giving us x greater than negative 5 minus 2 is negative 7, and subtracting 2 on both sides here and simplifying, again 2 minus 2 is 0, giving us x less than or equal to 4 minus 2 is 2. And now I graph both inequalities on the same number line, and because of the and, look for the intersection of the two intervals. X greater than negative 7 has an open point on negative 7, arrow to the right. X less than or equal to positive 2, we have a closed point on 2 because 2 is in the interval, an arrow to the left. Notice how the intersection of the two intervals, or the numbers that are graphed twice, are all the numbers from negative 7 to positive 2, not including negative 7, but including the endpoint of positive 2. So this is the graph of the solution. Using interval notation, we have the interval from negative 7 to positive 2. Does not include negative 7, but does include 2, meaning we have a parenthesis to the left of negative 7 and a square bracket to the right of positive 2. We can also say the interval is open on negative 7 and closed on positive 2. Next, looking at the compound inequality, we can see that two inequalities are connected by the word or. So we are looking for the union of the two intervals, or we are combining the two intervals. So first we have 2x plus 3 less than negative 2, or x minus 1 greater than or equal to 2. To solve for x here, we first subtract 3 on both sides. Remember, when solving an inequality, if we ever multiply or divide by a negative, we do need to reverse the inequality. 3 minus 3 is 0, giving us 2x less than negative 5, dividing both sides by 2. Simplifying, 2 divided by 2 is 1, 1 times x is x. We have x less than negative 5 halves, which is negative 2.5, or if we want negative 2.5. Or, to solve for x here, we add 1 to both sides. Simplifying, negative 1 plus 1 is 0. We have x greater than or equal to 2 plus 1 is 3. Let's graph both inequalities. X less than negative 2.5 has an open point on negative 2.5 because negative 2.5 is not in the interval. And we have an arrow to the left. Or x is greater than or equal to 3, closed point on 3 because 3 is in the interval, arrow to the right. Because we have an or, we are looking for the union of these two intervals, which means we combine these two intervals to determine the solution, and therefore the solution is both intervals. Open on negative 2.5, arrow to the left, or closed on positive 3, arrow to the right. To express using interval notation, to the left, we approach negative infinity. To the right, we approach infinity. The interval on the left is from negative infinity to negative 2.5. Neither endpoint is included, and therefore we have parentheses. Or, we can use the word or u for union. For the interval on the right, we have the interval from 3 to infinity. The interval includes 3. To the right, we have a parenthesis. Again, we can use U for union or the word or, both is acceptable. Now let's take a look at two special cases that occur when solving compound inequalities. For this first inequality, because of the word and, we are looking for the intersection of these two intervals. Let's begin by graphing the two intervals. Let's graph one in red and one in blue. For x greater than 5, 5 is not in the interval. We have an open point on 5, arrow to the right. For x less than or equal to -1, -1 is in the interval. We have a closed point on -1 and an arrow to the left. This looks like the graph of an or compound inequality, but it is an and compound inequality. And therefore, we are looking for the intersection of these two intervals. There is no intersection, and therefore there is no solution to this compound inequality. And therefore, the second number line with nothing graphed is the solution. And we often state no solution, which we can also express with the circle with a slash through it. And for the last example, we have x less than or equal to 4 or x greater than 0. For x less than or equal to 4, we have a closed point on 4 because 4 is in the interval, arrow to the left. And for x greater than 0, 0 is not in the interval, we have an open point on 0, arrow to the right. This looks like the graph of an and compound inequality, but because of the word or, we are looking for the union of these two intervals. Notice the entire number line is graphed at least once, and therefore the solution to this compound inequality is all real numbers. To graph all real numbers, we simply graph the entire number line. To express this using interval notation, again, to the right we approach positive infinity, to the left we approach negative infinity. For interval notation, we have the interval from negative infinity to positive infinity, which are not real numbers, which is why we always use parentheses for positive and negative infinity. I hope you found this helpful.